In this video, I'm going to talk about an isothermal batch reactor, which is a container with a fixed amount of solvent. And in this solvent, there is a compound A, and I'm going to say that it undergoes a reversible chemical reaction to produce B. So we have a kinetic constant K forward, we have a K reverse. Initially, there is only compound A in the tank, meaning that Cb, the concentration of B at time 0, is equal to 0. And I'm going to assume that this is constant temperature. We're going to neglect any heat of reaction and assume that the tank is either perfectly insulated or at the same temperature of its surroundings. Now, we should have some intuition from the system because from our general chemistry classes, we ought to recognize this as being mathematically equivalent to a beaker of compound A just sitting on a benchtop. So there's nothing going in and out of it. In chemical engineering, it may be customary to draw an impeller just to make it clear that the concentration is independent of position within the tank or the beaker, but that's actually not really necessary. If you have a homogeneous fluid, then you can probably make that assumption accurately even without stirring. We should have the following intuition. So we know that compound A will convert to compound B, not all of it, some of it, and the rules of chemical equilibrium ought to dictate what we eventually get. So once this system settles down to a state that we call equilibrium, then this is what we should observe. There should be an equilibrium constant capital K, which is equal to K forward over K reverse. And this should be equal to Cb at equilibrium over Ca at equilibrium. And the other observation that may not be so obvious to you is that whatever A is converted to B can be constrained by just an overall mole balance, right? So in simple terms, we can say that Cb at any time t, I'm going to say Cbt, is going to equal Ca naught, the initial amount of A, minus Ca at any time t. This is equivalent to, so this is also true at equilibrium. So once the system reaches equilibrium, you have Cb equilibrium, and this is going to equal Ca naught minus Ca at equilibrium. And so if we want to simplify this, we can say that K forward over K reverse is going to equal Ca naught minus Ca at equilibrium over Ca at equilibrium. So we can use this to actually solve for what Ca at equilibrium ought to look like. So doing a little bit of algebra, we can say that K forward over K reverse times Ca equilibrium is going to equal Ca naught minus Ca at equilibrium. And collecting terms, we can say that K forward over K reverse plus 1 times Ca equilibrium is going to equal Ca naught. And another way to put this, you can simplify this by saying this is K forward plus K reverse over K reverse. It tells us that CA equilibrium is going to equal K reverse over K forward plus K reverse times CA naught. So hopefully this is intuitive from what you learned in general chemistry, and it gives us a prediction just based on equilibrium considerations what we ought to get if we let the system evolve long enough so that it settles to a steady state. Now, in general, steady state is not necessarily the same thing as equilibrium. Steady state means that all time derivatives, d by dt of anything, is equal to 0. And we're about to set up a differential equation for CA as a function of time, and we're going to examine the behavior as dCA dt equals 0, and we're going to show that this is in fact what happens. That's the value you get at steady state. And for a closed system like this, where there's no material going in and out of the tank, no energy going in and out of the tank, it's at a constant temperature and pressure, it is true that steady state should be the same as equilibrium in terms of the behavior. So let's actually do a balance on A and B. In fact, I'm going to copy this just so that we always have it in front of us while we do the balance. Okay, so we're going to do a balance on compound A. So the general equation is input minus output plus generation minus consumption equals accumulation. Let's start with the accumulation side of things. So the amount of compound A in the tank is going to be Ca times V, where V is the volume of the liquid. We're going to say at time t plus delta t, minus CaV at time t, that's the accumulation. Nothing comes into the tank, so input is 0. Nothing goes out of the tank, output is 0. However, the chemical reaction does consume A and generate A. So the generation of A is going to be K forward CB, and the consumption of A is going to be, not K forward CB, it's actually K reverse CB, is going to be, the consumption of A, which is this term, is going to be K forward CA. And by the way, we have to look over an increment of time, delta t, so we're going to have CA delta, or delta t terms in each of the consumption and generation. So, by the way, I think I wasn't thinking about the units here. The units of the consumption and the generation are each in per unit volume terms, because concentration is per unit volume. So we actually have to multiply by V to get the total number of moles consumed and generated in that time increment. And now notice that every term here is proportional to V, the volume of the liquid. So we can actually cross out the V's. We can divide through, get rid of the V's, meaning that the dependence of concentration on time is actually independent of the size of the reactor. So you double the size, as long as the concentration remains the same, the time dependence of CA shouldn't change. So now let's make a differential equation out of this. We'll divide through by delta t. So Ca at t plus delta t minus Ca at t divided by delta t is going to equal k reverse Cb minus k forward Ca. We can take the limit as delta t goes to 0, as we always do, to define a derivative, and we're going to get dCa dt. And so I'll copy this over. And now I'm going to use what I used earlier, recognizing that Cb is really just Ca naught minus Ca. So whatever compound A is created, whatever compound A is consumed to produce compound B has to be conserved. In other words, whatever A is consumed becomes B, so the sum of Ca plus Cb has to equal Ca naught. Now, let's collect terms. So what we're going to get is dCa dt is going to equal C k reverse Ca naught plus k, oops, actually this is going to be a minus k reverse plus k forward Ca. And so let's now ask ourselves, so by the way, this is now the differential equation that we were looking for. Because I used this trick right here, I don't actually have to do a balance on B. In fact, this is a balance on B. So if you actually went through the same type of analysis on compound B, this would be the result, or something mathematically equivalent to that. So this is an equation that depends only on A, and let's ask ourselves what the steady state solution would look like. So dCa dt would equal 0 at steady state. So you can solve for Ca. So what this implies is that Ca at steady state is equal to let's move the Ca naught term to the other side. So it's going to be k reverse over k reverse plus k forward Ca naught. And what we wanted to check is, did this agree with our prediction based on what we know from chemical equilibrium constants? So let's confirm. In fact, it is the same. So what it actually tells you is that in this case, steady state and equilibrium concentrations are the same. So we haven't solved this differential equation, but at least we have confirmed that if you give this differential equation enough time to progress, the Ca naught will convert partially to Cb, such that it'll settle down to a steady state or equilibrium concentration defined by this quantity.